And we're ready for group 2, WMU main campus parking and transportation improvements. I do want to give a quick caveat before this group briefs. This is not a current project on the WMU facilities scope and so forth. It was an idea the students had because there is parking issues over near the College of Business. They want to explore those issues. They work with WGI, but this is not an officially sponsored WMU project. But they did work with an external client on the design to guide them through the process. So please don't go out and say, oh, hey, I just found out there's a new parking structure going in up by the College of Business, because that is not true. But it's a great student project. You'll enjoy this one as well. Noah, when you're ready, go ahead and share your slides and kick us off.
Going to clap or anything for the other group?
Oh, we can.
Nice.
Noah, you're on mute. Now you're not.
Okay, can you hear me now?
Yep, you're good.
Sorry about that. Hello, I'm Noah Busha, a civil engineering major and the project manager for this project. I'm going to be focusing on project background and transportation analysis.
Hi, I'm Kevin Dwyer. I'm also a civil engineering major. I'm a project engineer for this, focused on structural design.
I'm Parker Hood. I'm a construction engineer, discussing the construction management specifics as well as cost analysis.
Hi, I'm Jonah Henkel, and I'm a civil engineering major. In today's presentation, I'll be sharing with you how we came about our project's columns, foundation, and give you an overall project summary.
So today we're going to talk about our project, Western Michigan University main campus parking structure. To better understand what our project is, we'll give an overview of what our project encompasses, as well as why it is needed. Design criteria such as transportation, structure and member design, and an analysis of alternatives will be discussed to highlight the individual components of the structure. This will be followed by a load analysis, detailing our foundation design, as well as the sustainability aspects of our structure. Construction and cost analysis will accompany these topics, as well as an overall summary to provide our group's final design recommendation. So student parking congestion has been a rapidly growing issue on WMU's main campus, which is located 2 miles west of downtown Kalamazoo. Students that frequent the Haworth College of Business have significant issues finding available parking spaces, especially during peak class times. Therefore, these students begin to occupy restricted lots where they may get ticketed or towed. The purpose of this project is to design and develop a new multi-level parking structure that will be built to match the current and future parking demands while also improving traffic flow within the region. The design and layout of the proposed parking structure will amplify the sheer number of parking spots, while at the same time utilizing the existing surface lot 782W. So the current number of parking spaces within the existing surface lot 72W lies around 200 spaces, with our proposed design creating 734. Our 4-story structure is 310 feet by 185 feet, with a 12-foot floor-to-floor height for each story. By following code, the structure is designed to be ADA compliant. As a group, we do realize that that 740 spaces is quite a large structure, but our goal is to provide the appropriate parking infrastructure in order to restore some of the surrounding surface parking lots back to green spaces. This will not only enhance the campus community, but these lots could also be utilized for future construction as WMU continues to grow. So this is a concept level rendering of our proposed precast parking structure. There was not a supply demand analysis done, but this structure is of average size. Note this signature staircase, which will provide an aesthetically pleasing focal point to the structure. We considered massing of surrounding buildings to determine the appropriate height of the structure, as well as matching the exterior facade of both Haworth College of Business and Root Hall. The structure will not only provide parking for these buildings, but for the surrounding campus as well. By understanding the size of the car that we utilize this structure, we were able to determine the design of the interior parking elements. So our design vehicle, which we modeled the structure to accommodate, is a Ford F-150. This vehicle is larger than most passenger cars, but it will allow us to accurately encompass the system of vehicles that would potentially use this structure. Based on this design vehicle, we were able to determine parking dimensions such as parking module, angle of parking, and drive aisle width to meet the level of comfort that we strive to achieve. So a parking module is a span from the front of one stall to the front of the other stall across from it that you can see in the figure. Our design parking module is 60 feet with 90-degree parking stalls. Our drive aisle widths are also shown in the figure, and these are the widths of the lanes available for the cars to drive on while going through the structure. With a two-way aisle, the drive aisle is 24 feet. These interior elements satisfy a user comfort factor of B, which is very similar to highway design level of service, where it rates the performance of a system. With the student user group in mind, assuming there's very high familiarity of the structure and pretty large turnover rates, a UCFB is more than adequate for the structure. And due to these interior dimensions, our turning radius for this design vehicle is acceptable, which you can also see in this figure. So our design provides a layout that is user-friendly and ADA compliant, as well as providing an efficient utilization of the space. Again, everything that was designed revolved around the student user group. And in order to maintain a moderate to high level of comfort, we designed our stall dimensions to be 9 by 18, which is based on the industry standard. Accessible parking requirements was also a focal point in our design when determining how to structure each level based on ADA accessible parking stalls. For structures that have more than 501 stalls, the total number of ADA stalls are 2% of that overall total. So for our structure, we require a total of 15 ADA stalls. 12 of those are typical ADA stalls that have a 5-foot wide access aisle, which is shown in the figure. Code also requires that for every 6 ADA stalls, there needs to be a van accessible stall. Therefore, we included 3 of these throughout the structure that are 11 by 18.
Shown here is the ground floor layout, just to give a better understanding of the layout and geometry of the structure. We have 2 entrances and exits, one on the north end and one over on the east. The blue lines shown are the parking stalls, just to give an idea. These precast spandrels are to be 10 inches thick, which includes a 2-inch thick brick cladding on the exterior, which will match the aesthetics of all the surrounding buildings. The use of precast for these spandrels makes this an economical design, as major masonry won't be needed. These spandrels are 7 feet 3 inches tall and extend 3.5 feet above the surface in accordance with safety codes for both automotive and pedestrian fault prevention. These spandrels include a 8-inch by 8-inch button haunch, which will support the interior T-beams. There's also a 3-foot wide, 3-inch high wash along the entire perimeter of the surface, along the spandrels, which are there for design, drainage purposes.
Next up, we have our column design. Our columns were designed to support the loads and forces from above. The forces and loads that were used gave us a minimum column cross-section dimension of 2 feet by 2 feet. This minimum dimension goes for all the columns throughout the structure. Columns follow a predetermined column grid line as shown in the figure to the right. The columns were designed focused on modularity. The exterior columns have a special design feature in that they hold the spandrel in a pocketed column design. This allows for a seamless look along the perimeter of the structure, and the columns will not protrude on the exterior. Between the spandrel and the column, there is a 1-inch gap, which allows for easy assemblability, as well as allows for any sort of air during construction.
The double T-beams for the structure are precast with a 2-inch thick field top driving surface on top of the 2-inch thick flange. Our alternative is also shown below, which is a pre-top double T-beam with a 4-inch flange. The T-beams are what makes up the majority of the driving surface. They are 12 feet wide with 12 feet between the two webs. The field topping will have hand tool joints at each of the connections, and they are supported by button haunches on the spandrels along the exterior, as well as inverted T-beams that run perpendicular through the interior. So when analyzing our alternatives, we looked into 5 main categories, using different articles and resources, as well as conversations with different professionals, such as our sponsor, Greg Emke, came up with this data here. We decided that the pre-topped was more cost efficient because the entire T-beam is manufactured at once and you're not pouring a large amount of concrete on site. The field topped had better aesthetics because the joints can be uneven during placement, so the field topping can help to hide this. The pre-topped had a better construction timeline because there's no need to pour concrete on site for that driving surface. The field topped had less long-term maintenance because the connections can be protected by the topping, and the joint sealant can tend to last longer on the field top. The pre-topped had less environmental impact because the entire beam and surface are cast all at once. Although the pre-topped had more beneficial cost and construction timeline, we decided to go with the field topped for its aesthetics and reduce long-term maintenance.
So for the foundation we looked specifically at what the foundation would look like under a typical interior column found at one of the end of the light walls within the structure. The first step was to find the tributary area. When the tributary area was found, we were able to get our loads. The loads came from the materials we used within the structure, as well as loads and forces coming from where our project is located, because we have things such as wind and snow. In order to find the minimum footing area, we use the formula to the right, which takes the surface load that we calculated and divides it by the net allowable bearing capacity of the concrete. This gave us a square footage of 128 square feet. We then divided that, or took the square root to get 11.3 feet. We rounded that number up to 13. That would give us plenty of room for anything else to be added and gave us an overall footing of 13 feet by 13 feet. After the area was found for the footing, we next had to solve for the foundation's thickness. This was determined to be 28 inches. Within that 28-inch thick foundation is our reinforcement. We calculated to have 15 bars in the crossing formation each direction. The bars are to be number 7 bars and placed with a 10.4-inch spacing. It's important to know that the reinforcement also needs to have a 5-inch cover along the bottom of the foundation. It is important to also note that other columns within the structure may have a different requirement for the footing design.
So our structure was designed with high durability in the concrete to have a long service life. It also has an open frame, which can allow a lot of natural light to enter the structure, reducing the need for light fixtures throughout. The parking structure is to be constructed on top of a pre-existing lot, which can prevent the need for a total demolition in the surrounding environment. The structure is to be designed to be capable to support electric carports. However, this is beyond the scope of this project, but it is possible. There is some dead space throughout the structure that can't be used as parking spaces, but we decided they can be used as storage for alternative transportation, which can encourage the use of bikes and scooters throughout campus. We also have an area reserved mainly for maintenance and storage.
So considering our construction specifics, we our construction delivery method to be design build. Design build seemed to be the most logical approach due to the non-complexity yet urgency for our final completion time, as well as the ease of communication throughout the entire construction process. For the sake of our project, we're going to be practicing as many safety procedures as possible, no matter the probable chance for them actually occurring. All safety practices will be enforced with compliance of current OSHA standards. And given the compact size of our project location and surrounding features, our site layout needed to be as functional as possible to accommodate such a small space. The time sensitivity of our construction will also be constantly monitored, and all methods of fast tracking will have to be pursued with respect to safety. So we have created a project logistical plan in preparation for the beginning of construction. And as our progresses, it's projected that this layout may have to be adjusted and changed according to the phase or current activities on site. We have focused our layout separation to provide large enough space for all of our incoming equipment and materials, but most importantly, to accommodate the workers and our staff to ensure safe distancing from potential hazards and equipment while in operation. We found this layout to be the most practical in terms of overall coordination and workflow, as well as safety. So for our project completion, it is projected to be just about 12 months, starting in May of 2020 and ending the following year in April. The schedule was oriented to try and occupy space during the lowest period of student enrollment, which normally. So by starting in late spring, we could actually reduce our total interference with the fall and spring semesters, so we could achieve our ideal construction time during the summers. The schedule has a total of 44, 22 of which were on the critical path. This schedule goes into great detail on the fabrication of our precast structure, as well as all MEP, stairwells, elevator installations, landscaping, and finishes. Yeah, sorry, that was that one. Thanks. A cost analysis was also determined for the bare construction cost of the structure, and it was evaluated by the materials and the associated labor required for each precast section. The estimate did not include any other costs or activities into our calculations, although we do acknowledge that there are several factors that we should consider for additional costs. By doing this bare analysis, we confidently came up with a minimum cost that an owner might expect for the construction. We had used RS Means online estimation software, where we calculated the current market price specific to the Kalamazoo area required for the materials and work. In total, our structure cost came to be around $4.9 million, which we can then further break down into an average cost of $6,600 per new parking space built.
So to give an overall summary of our presentation, we chose to go with field top T-beams that allowed for higher driver comfort. We wanted the start time to be in the later spring semester, giving us around a 12-month construction period. We chose to go with precast material because that allows for a faster construction time and allows us to also order materials in advance. We wanted the structure to be a campus focal point. We have a staircase facing the business court and business college. The structure will also match the surrounding buildings, which is important to note. And having a parking structure on the outside of campus allows for a walkable interior campus. Overall, the parking structure will add over 500 spaces, alleviating the need for other surface lots around the area. Thanks.
In summary, we would definitely like to thank Dr. Haynes for his leadership and direction that allowed us to complete this project. Dr. Shao agreed to be our faculty advisor. Although we did not necessarily utilize this relationship, we still thank her for agreeing to be a part of our project. And lastly, our project definitely would not have been possible without the expertise of Greg Emke. So we'd like to thank Greg and his continual willingness to mentor us throughout the year. Thank you. Are there any questions? I'm sure there are.
Open up for question for the group.
Okay, this is June O. My first question is do we need that many parking lots in our campus over there? Do you have any?
Yeah, that is a good question, and that's something that we thought of. We did try to utilize that 72W and utilize half of that entire structure. So like I previously said, it's around 200 spaces now. The thought was that it could utilize future expansion of WMU as more students come here. And also we did mention that by creating a larger structure, we could maybe remove some other surface parking lots that could be used to build dorms or classes, or return to green space. So we do realize that it is a big structure.
Right, but those are all based on your. Yeah, but it's not based on the actual analysis. It's your assumption, because if you are investing a lot of money, we have to put the priority is more important. But in this case, I don't know whether if you are proposing this one, then university will actually accept the proposal or not, in terms of a cost and benefit side.
Part of Western.
Sorry, I can answer part of this. There was an outside research going on for the WMU master plan. Nelson Nygaard was running some data analysis on the number of parking in that existing lot. We didn't contact them to get their data, but I know they did have something going on for the master plan in that area as well.
Okay, the second question was, you are proposing the parking garage. I don't remember that you showed any parking lot design. Did you show us, or I missed?
We have our AutoCAD general layout. This is of our ground floor. We kind of skimmed through it. So from the east side, that is one entrance. North side is another entrance and exits. The blues represent our ADA stalls. And then our rendering is, like you said, we're trying to work off what we had. So this is what would sit on that existing parking or ground surface lot.
Right, because the parking garage, especially the university parking, we have to consider a lot of circulation, and then there are different types of parking garage design, but you didn't show any alternative and also just final solutions. So probably you may want to look at, there are maybe many different types of parking garage design, but probably you need to consider that as well.
We did consider not having an open layout where we would have window walls on the exterior. We kind of had to pick our battles with, we were spinning our wheels with how much we wanted to include, because our scope was what we wanted to include in it. So we wanted to kind of more focus on what was on the interior and these elements that we had talked about. I know this is just a kind of conceptual drawing that obviously this would have to change. This brick cladding might not be exactly what Haworth and Rood have now, but that would be our goal if this was to become a real project. But I do understand what you're saying, that it does have to match the current parking structures that we have.
This is Rex Bell. I have a couple of questions, somewhat related, but one is, could you say a little bit more about the decision to use precast versus cast in place? And related to that, the time analysis between the two and how you came up that precast would be significantly faster than cast in place. And the other question is the decision to be design build, to proceed on a design build basis. Were you talking about the entire project or just the precast portion? Can you say just a little bit more about that process? Thanks.
Yeah, which anybody want to tackle the first part of these questions? I'm going to go into the design build.
Going into design build parking.
Okay. Yeah, so in terms of the decision to make this project design build, we were focusing more on trying to meet our schedule demands. So we understand that there are other, obviously, delivery methods we could have went with, like bid build, and would have given us a much greater kind of range of options and prices. But in terms of accommodating our schedule, we figured that we would go with design build so that we could take away the bid phase so that we could go right into construction and have our communication between our designers and our builders. I mean, the whole team would have a lot easier communication throughout the process. So in terms of just the precast structure or the entire duration of the project, we didn't really break it up into those two sections to kind of analyze which delivery method we would choose. But I believe we would probably stick with design build throughout the entire process.
I can help answer the precast versus cast in place. One of the main reasons why we chose precast was because of where we live. We live in Michigan, so weather can have a lot to do with affecting cast in place. We know from stating it previously that there is a big congestion in that area with student parking. So we wanted to get that project started and get it completed. And with precast material, it gives you a quicker construction time, and sometimes it can give you a lower construction cost. So that was the main idea of going with precast.
Thank you.
I hope I answered your questions.
Any further questions? Oh, I'm sorry, go ahead.
Quick question.
This is Chaz. Oh, go ahead.
Okay, so since you did design of a structure part of a parking garage, I'm just asking you, what kind of structure criteria you used when you designed the structure part of this parking structure, like the strength, added, fact, serviceability, what are the structural criteria you considered in your design, structure design?
Well, initially we had to choose what we wanted to do in terms of our design element. We did utilize the expertise of Greg in terms of, from WGI, in terms of size we wanted, in terms of spandrels, light walls, columns. But in terms of our foundation, that's kind of more of a, and Jonah and Kevin, can you guys kind of back me up on this? We had to work with Greg on how we wanted to approach this.
I can talk about those columns you designed, the beams, did you consider the load? Did you do a structural analysis? Did you provide reinforcement? I didn't see those. You just present your final product. You didn't describe.
So we have more discussed in our final report, but for our presentation, we wanted to just focus on giving you the answers and a little bit about how we got them. So we wanted to focus on our foundation. With that, we took the tributary area and all the loads and forces coming from that.
Okay.
We kind of avoided the column section design and just went straight down to the foundation using those loads and forces though.
Okay, so more details will be in the report, right?
Yep, you're correct.
Again, we had to kind of pick and choose what we wanted to do. So we didn't get on that.
Okay, thank you.
Thank you.
Chaz, you have one quick question before we need to move to the next group?
I did. On the foundation, since we're talking about that, did I, when you were flipping through the see, there's 5,000 PSF, the loading? Just wondered if that was based on soil borings or kind of where that came from.
So we had to make assumptions for that. We didn't have any soil testing done yet. So that would have been one of our recommendations before the final project actually comes about, that soil testing must be done. So we just assumed a 5,000 PSF.
That's a pretty high one.
That was recommended by people who we had talked to. That's something we could look back into for the report. But
Okay, thank you.
All right, we're at 9:29, and thank you, everybody. Let's round of applause for that group. There we go. Thumbs up. All right.